So good morning, one and all again. So it's my privilege and honor to introduce Dr. Cher Ming to all our delegates today. And we rarely find such a distinguished person with such a rich profile. Dr. Cher Ming is currently the Director, Center for Reliability Sciences and Technologies, Changdeng University, Taiwan. His other current position includes Professor in Department of Electronic Engineering, as well as Institute of Medical Radiology Research, Changdeng University. He is also Chair Professor, Center for Reliability Engineering, Mingchi University of Technology, Taiwan. He is also researcher, Changdeng Memorial Hospital, Lingpu, Taiwan. Dr. Chemington completed his bachelor's in engineering in year 1984 from National University, Singapore, and pursued his master's and PhD degree in electrical engineering from the University of Toronto, Canada. He has completed his PhD in 1992. He has 10 years of working experience in reliability in the electronic industry, both in Singapore and Taiwan, before joining Nanyang Technology University, Singapore, where he was a faculty member since 1996. He joined Changdeng University, Taiwan in the year 2014. He has published more than 400 international journal and conference papers and holds 12 patents and 1 copyright for reliability software. He has given 16 keynote talks and more than 60 invited talks in international conferences. He has written 6 books and 5 book chapters in the field of reliability. His research interests include reliability and failure physics modeling of electronic components and systems, finite element modeling of material degradation, statistic modeling of engineering systems, nanomaterial and device reliability, and prognosis and health management of engineering systems. He is a chair of IEEE Singapore section, founding chair of IEEE Nanotechnology Chapter Singapore section, director of SIMTech NTU Reliability Laboratory, and senior scientist in SIMTech. He is currently a senior member of the American Society for Quality, a distinguished lecturer of IEEE Electronic Device Society on Reliability, a fellow of Institution of Engineers Singapore, a fellow and executive council member of Singapore Quality Institute. He is an editor for many distinguished journals, including IEEE Transaction on Device and Material Reliability, Scientific Report, National Nature Publishing, and many others. He is among the top 2% scientists in the world in 2022, published by Stanford University. He is also the chairman of Certified Reliability Experts. And more importantly, he has successfully executed several projects for the industry towards enhancing the reliability, and each and every project has resulted in savings of hundreds of millions of dollars for the industry. He is one of the go-to man for the reliability across the globe, and we have him here today with us. I welcome Dr. Cher Ming to deliver his keynote address. Welcome, sir.
Thank you for the introductions, and it is my honor to be invited by Cestras University for this talk. And yeah, I've been working in IC packaging since 1984 with Fairchild Semiconductor. And also, that's my beginning of my journey in reliability since 1984. So over the year, I've been getting a lot of experiences in this semiconductor, not only on packaging, but also on the wafer side. And so I would like to share my slide now. So good morning, everyone. And yeah, so this is my profile, and as has been introduced. And in fact, I was also given a tutorial talk in the RPS, and next year I'll be given a talk in the IEEE RAMS for the system reliability. Now, these are the few companies that I help in their reliability that will improve their reliability. So as was introduced, my reliability is not only on theory, but it's also indeed helps several companies to save a lot of money and in improving the product reliability. Now, reliability is something that people have overlooked. So many people are focusing on the functionality and also on the quality. And what functionality is that people want to make the product, for example, integrated circuit, having more and more functionality in the chip. And that is good. In fact, through this increasing in the functionality, and we enjoy the electronics today in our daily life. And quality, on the other hand, and so many companies are focusing on quality to make sure that in their production that the yield is good, meaning that all the product that they put in to produce will come out and able to sell. So these are the quality. And unfortunately, while many people are focusing on the functionality and quality, but many forget a new thing, not really a new thing, it's called reliability. As I said, that reliability is not new. In fact, reliability came before quality, but it's often being overlooked because um, it doesn't give you immediate benefit in a sense, but it will definitely destroy you if you do not take care of the reliability. What reliability really is that it ensures that whatever functionality that you design are able to last for the period, say 10 years in the integrated circuit. It will continue to provide the kind of functionality over the year. However, the quality approach that most manufacturing company has can only ensure that the functionality are there at the time when they ship to the customer. And the methodology to ensure that the product can continue to operate at the customer site for the rest of the year, up to 10 years or even 20 years, that is the regime of reliability. And so the quality and reliability are really different. And so today, what I want to look at is to look at the potential reliability issue with this advanced packaging. So, as I mentioned, that we all know that integrated circuit packaging is a crucial final stage, as the previous speaker has spoken. It is a crucial final state of semiconductor device manufacturing. Because the chip itself is fragile. Silicon die is very thin, very small, it's very fragile. And whereas the packaging is really to provide a protective case, so that this silicon wafer, although they can perform a very high functionality, but it need to be protected. It's kind of like our body, all our organ are very important. Our heart, our lung, and whatever is very important. But we need the bone, we need the skin, we need the flesh to protect all our organ so that we can function. It is the same thing that the IC packaging is a very important aspect for an IC technology today. And so this process is really transforming a bare die into a reliable, useful electronic component. So in a short, it will provide the protection, it provides electrical connections, it provides mechanical support, and it also provides a thermal management. And as mentioned, that today advanced packaging technology are 2.5D to 3D packaging. And this with this technology, it allows us to do the integration of multiple die within a single package. Therefore, it increases the performance and density. And so with this 2D, 2.5D or 3D, there is a heterogeneous integration, which means that we are putting different technology, for example, memory, sensor, RF component, etc., in a single package. Therefore, with this heterogeneous integration, that today the single package can have a good functionality and performance. To the extent that if you were to include other passive component as well, we can build a system in the package. And so that the whole entire electronic system used to be very big, can now be very small and in a single package. So by so doing, we can optimize the size, the power consumption, it can enhance the performance. So this is a roadmap for the packaging itself. In the 70s, it's a DIP, dual inline package. And then as go to the 80s, where I start my packaging work, and we have the QFP, LCC, leadless chip carrier, PGA, okay, plastic gate array. Then we continue on becoming a ball gate array from the pin to become ball gate array by the IBM. And then we also have the small outline transistor. And then in the year 2000, we already got the system in package. Okay, but still, you can see here that the diagram that the die are stacked up together and they're using the bonding wire. But then they can also do the BGA, and where there are number of pins, as you can see from here, they got so many pins on the die, and then there are solder ball on each die here, on each package, and then they will bond onto a green thing we call the RDL. which is it's a kind of, you can think of it like a small PCB, but then they try to spread out the lead so that the 2,000 ball together can spread out in a longer distance, and then they package it together, and this pin, this larger distance between the solder ball, can then bond onto the standard printed circuit board. So because of that, therefore you can make a very complex IC there with so many pins connected together, and instead of relying on the standard PCB to interconnect all these different transistors, they're using what we call the RDL to interconnect them together externally instead of on the chip. And further on, the 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 circuit itself can also interconnected through the standard PCB outside from here. Now, of course, a further improvement will be the wafer level CSP, meaning that you're bonding the die onto the wafer itself, and then the QFN, and uh, and and um and it's continue on. You can have a POP, package on package, instead of die on die, package on package. And then you also have a 3D IC to stack up the IC in a 3D format using the in between the connector through the TSV called the True Silicon VR. So therefore, you're making IC in a one die, but they actually stack up the die together in the IC itself. All right, so you can see that the packaging is very complex. It's getting more and more complex, and the goal is really is to move to a high performance, high density, low cost, and so this is what the goal is. So today, when we pick up a chip, you will never know that inside there could be many die inside. They are interconnected. And this 2.5D 3D packaging technology is really they're including multiple IC, and you can see that from the video here, you have the different chip itself, and then the RDL together with the silicon interposer, then you're putting onto the PCB itself. So this because of this 2.5D and 3D, it gain momentum as the ideal chiplet integration. And just on the previous speaker also mentioned about the chiplet, which is the present technology that we are looking at. And with this, as I said, that for a chiplet, we need to have a heterogeneous integration, which means that you're putting different technology onto a single package. This is what we call the heterogeneous integration. Now, they offer many advantages. For example, the data transfer rate can improve because the distance is shorter. It reduces the power consumption, and it enhances the device performance, and it occupies smaller space. But this heterogeneous integration also presents unique challenges because there are so many different types of material together, and they are also dissipating the heat. So therefore, you have to manage the thermal hotspot, and as they're operating at a different power level, and also as the heat come up, there'll be a different expansion because of different material, and this will causing a stress. So advantage, of course, is clear. Is the ultra high routing density, ultra high I/O density. It's almost like more than 400 microbarm per millimeter square. You can think about 1 millimeter square, 1 millimeter by 1 millimeter, the small area that contain more than 400 microbarm solder bump. And the I/O pitch are also scalable. So you can have either the homogeneous or heterogeneous memory, power, and optical integration. As today, optical communication within the chip itself is the in thing that people are looking for. And we need an interposer because we need to connect at different level. This interposer can also make it in such a way that they can be also function as a decoupling capacitor. So you will also have if you do it right, the package reliability will be good. They were able to meet the automotive requirement. And so today we know that in the IC we need a lot of memory, what we call the HBM, high bandwidth memory. And this memory are usually made using 2.5D to 3D to stack up together so that in a small area, we can have uh, many gigabyte of memory in a small area because they stack up together. It's kind of like a high-rise building that has so many people for the same square area. There are so many people are staying in the same area by stacking up into a multi-story building. And with this, that we are able to have a high-end CPU, high-end FPGA, and network switch. And today, the AI really require all these 2.5D and 3D. And so today we see the AI and the technology is getting higher, better and better. And they all actually really rely on chiplet, where 2.5D and 3D IC packaging are actually play a very significant role to actualize what we see today in the AI world. So this is an example of a system in package. You can have a different chip or package it into one package itself. Now, although the technology has advanced to such a level where we can have an entire system in a small things, and then we put so many different complex systems together to form a bigger system, and which can enable the AI to provide the kind of data that we want. And but then there are potential reliability issue. As I mentioned, that reliability is really very different from quality, but reliability is what is needed because you definitely do not make a chip that's so expensive, so functional, but only lasts for 1 year. You want it to last as long as they can, and this is what reliability is. Now, in order to ensure that all these chips are able to be service the customer, service the user for a long period of time, we need to understand that in such advanced packaging, what are the different potential reliability issue that can have associated with this packaging. Here is a table that lists up on the left column here. There are all the reliability issue that we can think of we are actually experiencing. On the right column is basically is the packaging type that will be affected by this reliability issue. I will go through each of them um, later on, but within each reliability issue, there are more issues within it. So in other words, the reliability issue for this advanced packaging is a lot more than what you can think of. It's very complex. And while people are thinking that the design of the IC is complex, while people are thinking about the manufacturing, the technology of fabricating the IC is complex, but what people do not know is that to ensure the reliability, facing with all kinds of potential issue, and to mitigate all these reliability issue is another complicated things. Okay, let's look at that each of them. In the thermomechanical stress, as I mentioned, that because of the heterogeneous integration, there are different material. When you have a different material, then the coefficient of thermal expansion will be different. In fact, when you go into the package itself, we don't even talk about the complex 2.5D or 3D. We have a silicon die with a substrate, with the molding compound, which is the polymer, we have a solder. All these are different material. So when the chip is operating, the temperature increases and therefore there will be CTE. The corresponding issue with this thermomechanical stress will be solder joint fatigue, delaminations, cracking in the die, in the molding compound, or warpage, and this will affect the yield, and also a whisker formation. Now, you can see there are so many issues even within a topic itself. All right. Now, I don't have time to go through every one of them, but I will pick up one from each group to have a discussion. Now, whisker is something that may not be very familiar by many people. What is whisker? Now, thin whisker are electrically conductive. They are really a crystal of tin that is grown from the surface from the tin itself. And so they are needle-like and they can grow to the length as long as several millimeters. In today's world, we are talking about miniature and integration. Several millimeter meaning that you expand to several die, several contact. And the growth actually is not entirely, not fully understood. In fact, we know that it is a compressive stress that causing the thin crystal to grow out, and especially in the high temperature and also the humidity. And this thin whisker, although it's very tiny, it can carry the current up to 25 milliamp, and I can sustain a volt electric field of several tens of volt, maybe like 0.5 volt per millimeter before it's burned out. So in other words, it can cause some havoc. It can cause some problem because it can carry the current, it can sustain the voltage. It's not like the moment it forms, it burn out. So when you carry the current, causing a short circuit. And this short circuit can be intermittent because the moment the current passed through, it melted and it stopped. But it can also be sustained. So this is especially true for the low current circuit, because for the high current circuit, the current is high. The moment the whisker is formed, it will melt almost immediately because of high current. However, today's IC, we are emphasizing on low power. We are emphasizing on the low current. This will mean that the thin whisker that is formed will sustain, and therefore it can actually pose a very serious threat to the low power circuit. What material can form whisker? All these materials commonly used in electronics like lead, tin, aluminum, copper, zinc, silver can all form thin whisker. Now this is a cross-section photo of the thin whisker. You have the solder on the copper itself. The grain structure of the tin are laminar. So when they have a compression stress from both sides, because of the stress, this grain of the tin has to go up, and then this will form the thin whisker. Now you can form a thin whisker like this. You can really see it under the electron microscope that the tin actually pop up from the surface. If it is too long, it may bend itself. All these are indeed the true picture of the thin whisker that's formed. So you can see the solder ball itself, and today's the standard microbump are using the thin silver copper, we call the SAC solder. When you have a stress, you can see that the thin whisker coming up. Okay, you can see that the thin whisker is coming up from here. And as I said, that the thin whisker can be long. It will continue to grow. Before you know it, it will not cause any electrical problem initially when it grow. And so therefore the circuit will function as per normal. But the moment when the thin whisker is growing to a certain distance, it will short circuit to the nearby solder, and the whole thing will get short circuit. It will malfunction, or even it can cause burning. And so this is a very serious issue in today's IC. Why is serious in today's IC? Because in the early day, we using a lead solder. When you put lead in the solder in the thin whisker is suppressed. But the moment when people change to the lead-free solder, thin whisker grow in an amazing way. And so without being a good understanding, when people change the lead solder to the lead-free solder, thin whisker become a very serious reliability issue, even until today. And so it's really the cause of it is really due to the internal stress, thermal cycling, also the intermetallic formation between the tin and the copper that were causing a stress in the tin itself, and oxidation as well. So it's causing a short circuit, component failure, and before it happens, maybe you start to see a lot of electrical noise, or sometimes even the intermittent operation. So it is a safety concern because it causes short circuit. And the way to mitigate, of course, you put the alloy in. As I mentioned, if you put lead, it will be everything is fine, but lead cannot be used. So people are trying to look into putting different alloy in the thin solder. And for example, the common SAC 305 or even 105 is not immune to the thin whisker formation. And surface treatment, for example, by coating it with some kind of coating, of course, it can prevent the thin whisker from forming. But you got to remember that the thin whisker is as small as a needle. So even if you coat something, the needle is so sharp that it can poke through the coating and it will form. You cannot eliminate, but you can only prolong the formation. Of course, the best way is to release the stress because the root cause is the stress. But how do you release the stress? As there's a different thing because there's so many solder together. All right, so that's one of the reliability issue. Then there is interconnect reliability. There's electromigration, stress migration, corrosion. Within this, as I mentioned, that today in the heterogeneous integration, you have the RDL, which stands for redistribution layer. You're causing crack because of the stress migration. The TSV, just like I mentioned about the 3D IC and the micro bump, can have void and therefore causing open circuit. The copper interconnect in the tiny PCB inside the chip itself, because the line width of the copper will be still very small, unlike the traditional PCB, there will be electromigration. And also during the bonding, during the solder bonding, and because today's IC are using an ultra low K, so when you try to solder the solder bump into the RDL itself, the mechanical force can cause a crack in the underlying dielectric. And solder, of course, itself is so tiny that solder electron migration is a problem. Now, TSV is what we call true silicon via. And I did a study on this true silicon via in 2010, where you can see that when you start to pass through the current, so this is true silicon via. This is interconnect connecting to a true silicon via. After a while, you can see that there will be a crack forming, and then you continue on, and finally this crack, this aluminum, this could be a TSV, so copper, this crack can form, and in the end, this connection from the circuit are no longer connected to the TSV, and therefore they're open circuit. So this crack is not because of mechanical stress, it's purely due to electromigration itself. Now the EM and the solder, you can see that let's say you have a solder, in the early day where this lattice solder is still allowed, you can see that this is a solder ball. I got aluminum. And again, if I were to do a finite elements, I can see that the current distribution will be very concentrated at the corner here. And if I were to remove the aluminum strip, you just look at the ball itself, you can see a very tiny stress concentration here. This stress concentration, due to the thermal gradient, in other words, this place here has the highest thermal gradient. This will cause the electron migration to progress. And the thermomechanical stress also highest there. So this experimental work that people have done. You can see that for the different type of copper at different type of solder, as you go on the time from 0 hour to 300 hours, you can see that they're always at the corner side, as I shown from the finite elements analysis, that there will be a stress concentration here. And this stress concentration causing electron migration to move, and therefore they will move inward to the center. In the end, you're causing an open circuit. In other words, the solder is there, but there's no electrical connection. So it will happen 300 hours, not long. We expect the IC to work for 10 years, 15 years. So how can you make sure that this will not happen? Now, these are the physics. You cannot beat against the physics, but you got to go around the physics. Okay, you cannot change the physics, right? But then engineer has to go around the physics by understanding the detail of the acquisition physics. Now, thermal management, because of so many chips are there with a high power density, and the chips are so small, yet they produce the power. So they are limited thermal path. So these are the different issues they will have. One of them is the IMC formation, and this is the what IMC is the intermetallic compound. When the solder are connected to another metal, whether it's copper or whatever, they will form an intermetallic compound. This intermetallic compound is necessary to have a good soldering. However, when they form, they'll continue to grow. After the process, after the reflow, they will continue to grow, and due to thermal aging and cycling. And as you can see here, that you can see from the diagram here, you can see that as 24 hours, you can see that there's intermetallic. As you continue on to 100 hours, this intermetallic will grow larger and larger. And the main intermetallic is Cu6SN5. But as you continue to grow, you can start to see another new intermetallic, Cu3SN. And this Cu3SN will becoming thicker and thicker. The problem with this is that the Cu3SN is very brittle. It's almost even more brittle than glass. So what it means is that when it is so thick and they occupy the interface, so it means that when you drop it, it's almost like you're throwing a glass onto the floor, and therefore this whole thing will collapse. And so this very thin IMC layer actually will form, as you can see, and therefore you will causing it to be weakened, and so that in the end the solder depart. But you won't see it because everything is inside the package. So you'll see that your package is not working, but because of this. Now, thermal aging is another thing that, especially for molding compound, and so this the thermal aging is no. Before we go to that, as I said that the Cu3SN is very brittle, so when you drop, it will actually break. You can see that this is the experiment people have done. They put the solder, they do the thermal, they put it at 125 degrees C for 10 days. The drop, the 50% of the samples will drop, will fail, okay, will be still quite high. You need to drop, you need to throw about 90 times before they break. But then as you continue on aging for 10 days, it will drop immediately to, you just need to drop 20 times. 50% of the solder will already give way. If you're aging to 40% at 40 days, it's almost like one drop is gone. Okay. So this is the reason, the reason behind it is because of the formation of the CN3SN. And you can see that it's totally broken. And if you were to go to the further analysis, you can see that the CN3SN, you can see that they actually form a lot of void. And this void here, as you go over the time, okay, for 150 degrees C, 3 days, this void will form together in a line. In the end, it will form a line, and the two things virtually detach electrically. But mechanically, because they're still inside the package, you don't see them falling apart. But basically, in terms of functionality, they're gone. Okay, you can see that they're forming a line. That's why in 125 degrees C, 40 days, the one drop, everything is gone. Okay, this is what you can see. All right, so there are a lot of study on that. It is a very good understanding of what's going on. So the IMC is one of the important things in the packaging that we need to watch out for. Electrical reliability is that there are always dielectric in the IC itself. And this electric, when you have a high current, when you have a voltage overshoot because of the parasitic inductance, they're causing a voltage overshoot. All these things will cause the electrical noise, first of all, power delivery, and therefore signal integrity will be affected. They will also causing the dielectric breakdown in the insulation layer because of the voltage overstress. So, and ESD, of course, is doing handling. But once you assemble itself, if your circuit design, whether it's in the RTL or in the PCB, if it is not properly done, there will be a parasitic inductance that causing a voltage overshoot that will cause a high voltage to be applied to the IC itself. And as you know, that the MOSFET will have a dielectric, or even in between the metal interconnect, they're dielectric as well. So this dielectric, because of the high voltage, will break down. And also this dielectric, during the bumping process, will also cause cracking. You can see that, for example, this is silicon. I got a solder bump. When I do the bump, when I do a soldering, it's almost like first of all, I got to attach the chip onto the substrate itself, and the solder will start to melt. So first of all, this is the vertical force. As the solder start to melt, they actually have a pulling force. As a result, because of this force, it's creating a moment um, on the surface of this solder bump, and this moment will cause a crack underneath because of the low K dielectric, which have a very weak mechanical strength. And you can see that there will be some you can actually measure or even to evaluate how good they are. All right, so there are different methods. I won't go through it. You can see that there will be a crack coming up, failure, because of this crack even before the operation of the chip itself. It means that the moment you flip chip, bond the chip onto the substrate itself, because of the force, you can cause a crack underneath the interconnect. And unless you lift up the interconnect, you weren't able to see that. And this is actually happening. Now, another thing is the moisture and contamination. Packages are supposed to be protect the die from moisture and contamination. But then if your sealing is no good, the moisture or the contamination can get in, especially during the reflow process. Because of the different thermal expansion, there will be some gap, and this can go in. And also, if the package itself or the PCB itself has some moisture inside, and then during the reflow, the high temperature become vapor, they can producing what we call the popcorn effect. Okay, so but furthermore, when the moisture get into the between the solder bump, it will also cause the dendrite formation. And then there's a corrosion, and I won't go into detail because of time limitation. Corrosion or electrochemical corrosion will be there. But the dendrite is what is going on. When you have two solder there with the moisture, because you apply different electric field, the solder will start to migrate in the moisture from anode to cathode, and in the end, a short circuit. So this is indeed the SEM picture for the dendrite growth. In fact, it is the solder from the right side going into the left side and deposit. So the tree is growing from here, but the solder is actually moving from the right side to the left side. And this is causing a short circuit. Material degradation or thermal aging, as I said, the molding compound is a polymer, and they will keep on moving as you continue to operate. And there are other issues as well. And this thermal aging will cause the polymer, because when you do the molding, the polymer is in the molten state, in the rubbery state, and it is above their glass transition temperature. Then you cool it down. As you cool it down, if you cool it too fast, there are no time for it to reach the thermodynamic equilibrium. So material always want to go down to the thermodynamic equilibrium, and therefore they will start to move, so that to reach the thermal equilibrium stage. As you start to move, and what happens is that they will cross one another, the polymer change, and then in so doing, okay, because they want to release the excess free volume, is they entangle with one another, this polymer in the molding compound. And therefore, their TG will also decrease. And not only the TG decreases, they also, because they become denser, because they entangle with one another, become stiffer, and they become brittle. So when you come to brittle, meaning that when there's any impact, they will cause a crack. a slight heating, instead of heating on the glass, you have a crack. And this crack will allow the moisture from or the contamination from the environment to get into the die, and therefore causing the failure. Okay. And another thing is the delamination and adhesion loss. Thermocycling, because of the operation of the chip, you'll go heat up and reduce, heat up and reduce. There's a thermocycling, and the humidity can also get in. They will cause delamination and adhesion loss. So I won't go into too much of that. You can see that this is a delamination at the solder end. This is a solder. You can see that there's a crack in the solder. Why there's a crack? Because of the delamination. This delamination will try to pull it up and therefore causing a force exerted upon the solder and causing a crack. Sometimes the delamination happens between the solder and the copper pad itself. And then, as we know that in the chip we have a wire bonding of solder bump and also the micro bump, and all these will form an intermetallic as you've shown, as I mentioned before. And the wire bonding can also causing a break, and all this will causing problem. So, and when you come to the heterogeneous integration, we are combining the die of the different process. So when you're putting a die onto the substrate itself, there are micro bump. The misalignment of the micro bump can be an issue because the dimension is very small. Therefore, the tolerance has to be very good. And also, because of different material, it can cause warpage if your design layout are not proper. So this is a picture of the misalignment of the bump, because this die are supposed to connect to the other die. And there is a misalignment. How small is the misalignment is in the micrometer. So unless you have a very good tool that you are ensuring that there's not, I mean, we are talking about tolerance of micrometer tolerance. Because if that's the case, the stress along prolonged operation, the stress will be non-uniform because the current flow is not uniform. So this part here will not have current flow because the most of the current flow will be in the middle. It will be heat out. Whereas the surrounding will not be heat out. Therefore, this causing a thermomechanical stress. In the end, the crack will form, and therefore you will see a crack line across it. So in conclusion, you can see that there are so many potential reliability issues just on the packaging itself. And although we enjoy the functionality, but we expect that this functionality will also give us enough time to enjoy it. But then if you fail so fast, if you do not look into all these potential reliability issue and address it, your package won't last long. So in the end, the time of enjoyment will be very short. Or put it more realistically, no customer will want to buy from you because your chip is not reliable, despite your functionality. So therefore, we need to have a thorough study on the reliability associated with the package. Not only understand the physics of reliability, but also able to understand how to perform the failure analysis and then how to evaluate the reliability of your die with respect to all the issues that I mentioned before. So with that, I conclude my talk. Thank you.
Thank you, Professor. Thanks for this great session. So we have a couple of questions. So there is a question from Mr. Arindam Pratur Sharma. So his question is, how can we map DFT and failure analysis with reliability issues seen across products? As a test engineer, what special precaution can be taken from the DFT and post-silicon angle?
Well, basically from the test flow, you won't able to see the reliability issue. The reliability issue must be tested under an accelerated life test. Because if you see the failure during the testing, that is a quality problem. And the problem with the reliability is that it will only happen after some time. And so what we do in the reliability is that we'll take some chip and we perform the accelerated life test, meaning that we increase the stress. And so with this higher stress, it will mimic the situation by compressing the time. So through this special design reliability test, and we are able to see that whether a die can actually operate for 10 years and what kind of failure mechanism would it be. So you can't really surface out the reliability from the test flow itself.
Okay.
So design for testing is more for the quality rather than for the reliability.
Okay. Okay. So there is one more question. This is from Mr. Raymond Roach. How to remove or avoid the viscous growth which causes short circuit in the components?
Well, this is a $1,000,000 questions. This is the question that many customers want to know how to remove the whisker, because whisker at one point has been suppressed, and recently I have a lot of customers reporting to me that whisker is growing again. Whisker is really due to the mechanical stress and also the corrosion. So if the corrosion are able to, if you can prevent the corrosion by having a proper shielding, then the whisker formation, the way to mitigate the whisker formation is to reduce the stress in the solder. So there are several ways to reduce the stress. For example, by using thermal annealing, and you can reduce the stress. And also, as I said, that people are using some coating so that make the needle, the whisker, more difficult to come out. And the ultimate solution, of course, is to add in some more uh, metal inside the solder. Because as I mentioned, that for the leather solder, there's no problem for the whisker. The reason is that when you add lead, they change the microstructure of the solder, so that when under the compressive stress, the solder grain can actually rotate instead of going out of the surface. So therefore, people are investigating how to put in what kind of metal. Now we cannot use lead. What kind of metal can replace the lead so that you can change the microstructure of the solder instead of like the coroner, and they make it to be more like a round shape of the microstructure, so that you can imagine that if you have a stone, if you stack out several mini stone and they are round with some gap. So under mechanical stress, they can kind of rotate itself, and therefore, instead of popping up from the surface, they can kind of adjust itself and accommodate the stress. However, if you don't, there's only way to reduce the stress is by going out the surface. So the ultimate way to solve it is to find the substitute of lead into the doping into the solder itself. But in the interim, we got to make sure that the stress in the solder is lower through annealing and using the coating itself.
We sincerely thank Professor Cher Ming Tan for his presence today during the inauguration, as well as for delivering a keynote address. On integrated circuit packaging and reliability. So I take this opportunity to invite Professor Cher Ming to Sastra University and visit us and have interaction with us, so that we will be having the benefit of listening to the 4 decades of wisdom for a more time during your presence in India. So on behalf of the organizing committee, our university, as well as Lungwa University, we express our sincere thanks for your talk. Thank you very much, sir.
Thank you. Thank you. Yes.
Thank you.
All right.